want to introduce the next speaker, Melanie. I kind of think of her as a Postgres scientist. She's very analytical and rigorous, and she's worked on many different parts of Postgres, but is now mainly focused on the I/O layer. And she's going to talk to us about a feature she developed for Postgres 14. So Melanie, if you're ready, the screen is yours.
Thanks. I'm going to talk about developing a prefetch algorithm for Postgres. And so this is something that we've been working on right now. And it's actually I've developed it for the asynchronous and direct IO patch set that's proposed for, probably for 16 now. So prefetching is basically preloading data from either permanent storage to memory, or sort of the more well-known example is loading data from main memory into the CPU cache with the goal of decreasing the effective experience latency for the user. So in the case of storage prefetching, most applications are using buffered IO. So the kernel is managing bringing data in from permanent storage to memory for the applications and doing read ahead. But some applications have more rigorous needs, and so they might actually do their own storage prefetching. So why would they do that? I think the main reason is that applications have superior knowledge of their data access patterns. So a good example of this is if you do a Google search and your web browser, the only content that you're going to need next is one of the pieces of content that's linked in the links that are returned from your search. So the web browser is going to know much better than the kernel what needs to be fetched next. And in general, application prefetching is going to be used when there's certain performance guarantees that are required. And so databases are an example of IO-intensive applications with performance requirements. And there are different kinds of prefetching. So many databases have a direct IO, and some of the benefits are that you don't have to keep the data in the kernel buffer cache and the database buffers. But prefetching can be irregular prefetching for things like certain data structures, like doing a B-tree lookup or something like that can be complicated. The most simple kind of prefetching is sequential prefetching. So just imagine a sequential scan and you're going to read in all the blocks in order. So the question is this is pretty simple. Why would you need an algorithm for this? Because I'm talking about developing the algorithm. And the reason is because your query for that one table isn't the only query that's going to be going on your Postgres instance, and maybe not on the box in general. So you need to make sure that you decrease memory usage and only use as many buffers as you need for the blocks that are, going to actually be read, and you want it to sort of be just in time or have a little bit of a buffer. So the goal is to keep the number of buffers being used, or the memory being used for the query, as low as possible while having the consumer not wait at all. And that's really, a consumer might be a user-initiated query, but it also might be a maintenance process like vacuum or something like that. So the algorithm's goal is to be able to bring those buffers in at the right time. Now, currently, prefetching is in limited use in Postgres. So Postgres uses buffered IO right now. But there are cases where, like bitmap heap scan, where it's worthwhile to actually do some prefetching because the kernel has no way of knowing the specific blocks that you're going to want to scan for a bitmap heap scan, because you do the index scan first, figure out the exact blocks, and then use that to go scan the underlying relation. However, with the proposed direct and asynchronous IO patch set, if you use direct IO, you have to have prefetching. Otherwise, every single block that's requested by the consumer is going to experience the full latency of the storage. And of course, you have the syscall overhead for every request also. So in that branch, there's, of course, there is prefetching, but there's some limitations or issues with the current algorithm. So it just uses a constant multiplier, like fetch this many blocks, okay, fetch double that, fetch double that. And it's a coarse heuristic. Also, it's not adaptive to different workloads or storage types. So we decided we wanted to develop a new algorithm, and some of the challenges around that are that, if we said, okay, let's take Postgres and let's just develop some kind of benchmark or come up with some workloads that we want to try our algorithm and see if it's effective. And you have to run them for a long time to get results. You have to make sure and carefully configure the file system in the database to make sure that you're actually testing the algorithm and not just testing, whether or not you have this or that configuration. So you have to make sure the bottleneck is at the right place. And it also takes time, and you have to get all those different types of storage, and coming up with the workloads is not, wouldn't really be useful to just run pgbench, for example, if you're trying to isolate a particular part of the algorithm. So I wrote a simulator, and the idea behind it is that you can quickly run a lot of different scenarios, try out different workloads, and emulate different storage types, systematically building up the complexity of the algorithm. So the simulator its core abstraction is a pipeline, and IOs go through different phases, and I call them buckets. So I might say the word bucket, and that's basically, it just refers to a phase the IO goes through. And each phase has a set of rules that underlie how the IO gets moved to the next bucket in the pipeline. And you might see on some of the charts that I'm going to show at the bottom, it says ticks, and that's just sort of the abstraction that I use to quantize time. So using the simulator, basically first I start with modeling a storage system. I'm going to go through an example of one, but it's useful to compare or to actually model the mechanics of specific mechanics of different storage systems to make sure that the simulation is realistic. And then I model the workload, and I'll talk more about what that involves. And then you sort of start with the algorithm and look at the output. So I'm going to walk through how I modeled IOU ring. So this is kind of the first step. So IOU ring is a pretty recently developed async syscall facility in Linux. You map basically just map a ring buffer into user space, and it has several benefits that make it good for applications that are trying to do asynchronous system calls of various kinds. And so the characteristics of IOU ring that were useful to model, I'm going to go through those right now. So when you set up the rings, there's a fixed number of buffers that you actually configure it with. And that's a cap. I mean, you can't have more in progress IOs than that. And because the rings, there's one for submission and completion, that means that an IO you're taking up one of those buffers for the full duration from submission through completion. So while it's in flight and everything. So the first phase, an IO, you only can basically add more IOs if the global capacity has not been hit, so that global ring size. The next phase is meant to model the a threshold. So one of the main benefits, or one of the big benefits of IOU ring, is that you can amortize the cost of the system call to actually submit the IO. And so you can say, okay, every 5 IOs that I copy into the submission queue, then I'm going to call, IOU ring submit or whatever. So that is a mechanic that is interesting to model here. So this one will only move IOs into the next phase once you've hit that threshold. And then the third part of submission that I wanted to model was the overhead of actually making the submission syscall. And so the way that works is that IOs are moved to that bucket. They're only moved into the next phase once the duration has passed for which what represents the submission overhead. Now that we've progressed into the part of the storage model that models actually the device, physical device, so max IOPS, this is an important cap. And so when you define the simulation, you define a storage latency, and you specify a max IOPS. And those together, when you multiply them, that's basically the number of concurrent IOs you can have. So you can do that many IOPS at that latency. IOPS is IOs per second. So if you try to push more IOs onto storage, I mean, so it's different for physical storage versus cloud storage, but the basically the idea is that, you know, the system can only service that many IOs at a time. So this bucket basically, if you try to add more, so all the IOs that it contains, it's only going to move into the in-flight state if it's not at max IOPS. And then the last phase models IOs actually being in flight. And this bucket's mechanic is that the user-defined completion latency function is similar to the submission overhead. IOs in this bucket will not move to the next phase until they've been in this bucket for that duration. And one thing that you can do if you're looking for what's a reasonable value for storage latency is you can use this tool called FIO that you can measure for, say, a physical device, a cloud storage, different types of storage, what reasonable latency is for a sequential write, a sequential read. Like, you can check the different types of latency. In this case, you'd be most interested in sequential reads of like a larger size block. And then you can use that in your model. So the next step is to model the workload. And when you're modeling the workload, pretty much the only thing that you have to do is define a consumption rate function. So this is basically standing in for the query or set of queries or maintenance process that we're going to be prefetching for. And the idea is that the consumption rate specifies how much the workload, how much IO it wants. So it may want 1,000 IOs a second. And the difference between what it gets and what it wants is waiting. So if it wants more IO than it's able to consume, then it's waiting. And so this, the consumption rate is a function. So you can say, hey, every 5,000 ticks, the consumption rate's going to jump up, or whatever most sort of best models your workload. So for example, if you have a nested loop join, you might have the outer side is doing sequential scan. You might have it consume IO every 100 milliseconds. If you have a super slow, like computation intensive inner side to do. So depending on what you're trying to model, you would change the consumption rate. And then the last phase is actually to work on the prefetch algorithm. And there's two components to the defining a prefetcher in the simulator. One is a function that determines the size of the prefetch, so prefetch 10 IOs, and the frequency, how often, so every X number of ticks. And then a means of adjusting the algorithm. So the whole point of this is to have feedback adjusted prefetching. And so that is the way that you sort of adapt the prefetcher then feeds back and determines the amount of prefetching and the frequency of prefetching. Now, looking at the output of the simulator, so you've just defined the workload, defined the prefetcher, defined the storage, and modeled all of those. The output, once you run the simulation, are charts. And it's much easier to look at it visually than to look at numbers. And so before we look at some examples, I want to go over what a good result looks like. So as I said at the beginning, you want as few extra buffers occupied as possible. So you want to use as little memory as you can if you don't have to, but you don't want the consumer to wait. So you don't want to be waiting on IO, obviously. And so you also want to make sure that you're prefetching or requesting not more IOs than you can consume, and that you don't have IOs waiting to be dispatched to storage if you have slow storage. So just sort of as a visual for this, if your prefetcher is working well, then you will have a small buffer of completed IOs that are waiting for the consumer to pick up, and the consumer doesn't have to wait. You're utilizing or as much of the storage capacity as you need. So your in-flight IOs are pretty high, and you don't have a backlog of IOs that your prefetcher has that has requested, but are not in flight because the storage, basically they're being throttled. So in a prefetcher that's too aggressive, in this case, you might see a lot of completed, not consumed IOs, and they're just like building up. And a prefetcher that's too aggressive, but sort of you're bound by the storage being too slow, you might see the prefetch rate is going up and up. More IOs have been requested, but the number of in-flight IOs is actually not going up. And there's not extra IOs that are completed and not consumed. That'll stay around 0 because every time an IO is completed, the consumer will consume it. So what's a baseline here? There's two ends to the spectrum, and on one end is completely synchronous. So a consumer requests something, an IO, and at that point, then it's like a demand miss. The database goes and makes a syscall and requests it. And you can see here that remaining, so in this case, the volume of IOs that was going to be fetched was 200. And so remaining is kind of like what the prefetcher has yet to request. And so you can see that's going down, and completed not consumed stays 0 because every single time an IO is finished, the consumer picks it up. And you can see that this takes like 100 milliseconds, I think that is. And now let's compare this to the complete other end of the spectrum. This is, so these are on the same axes. So this is the opposite end of the spectrum, a prefetcher that just requests all 200 IOs right out of the gate. So you can see that what's happening is that the number of completed but not consumed buffers is quite high. So as the IOs are finishing on storage, they're then building up in that backlog of completed not consumed buffers. And you get up to like 140, 150 buffers that the consumer is not able to keep up with. But this, you can see, takes closer to 40 milliseconds. And so somewhere in the middle is what we want. We want an algorithm that keeps the number of completed buffers pretty low or even, and but still performs well. So here you can see that the number of completed not consumed buffers never exceeds about 20, and but we're also finishing around 40 milliseconds. So what we're looking for is a one-size-fits-all prefetcher. We want it to work for local storage, cloud storage, different storage speeds, different workloads. We want it to work for analytical queries. We want it to work for all different types of workloads, the same prefetcher, meaning like we don't have to configure it for local storage or configure it for cloud storage. And the catch is that we don't know what the max IOPS are. I mean, sometimes you do when you're you sort of provision a machine, you might know. But the goal is to have a prefetcher that doesn't introspect or have all the stats about the different about the environment, but uses feedback to adjust. So just to kind of set expectations or remind everyone, cloud storage tends to have higher latency and than sort of say fast local storage. So I model two different types in the results, and these are around the latency and IOPS that I defined. So you're going to see typically, though you can provision cloud machines of different sizes, very few, you're not going to provision something with more than 20,000 IOPS probably. So yeah, just to kind of give you some calibration on these speeds. So we also want the prefetcher to be adaptive. So we want it to actually change when the workload's consumption rate changes, the prefetch rate. And we want the prefetch rate to also adapt to if other workloads, competing workloads, cause there to be less available IOPS or higher latency. So this is an example of adapting to a changing consumption rate. The orange is mapping the consumption rate. You can see for the first 5,000 ticks, it's around 2,000 IOPS. And then suddenly it shoots up to 5,000. And you can see that again around 20,000 ticks. And because what the prefetcher is actually doing is it's increasing the number of blocks requested. And you can see that the in-flight IOs edges up and sort of the average goes up. So by the time that we're requesting 10,000 IOs per second, the number in flight is higher. And just another view of this, you can see here. So the done line is what the consumer is consuming. In this case, we're bound by the consumer. So the storage is fast enough that we're not, that we can see in the done line, the increases in consumption rate. So around 5,000 and 20,000 ticks, you can see that the line adjusts, but the number of completed not consumed buffers stays relatively stable. And you can see that the remaining line, that's like what's being prefetched, kind of mirrors the done line. On the other end of the spectrum, if you have slow or cloud storage, you're going to be bound by the storage, right? So the consumption rate doesn't matter as much because you can only get so many IOs in flight. And so in this case, what you're looking at is the orange is the prefetch rate. And if the prefetch rate is too high for the storage, then you're going to end up requesting more blocks than can be in flight on the storage. So what you see at the beginning is that the prefetch rate is going up, and because it's adaptive to feedback, it goes up and down. And then it sort of starts to settle down, and right around I think 60,000 ticks, or it starts to go back up again. And that's actually because I use a recency mean that is weighted to favor adaptation to more recent measurements. And so in this case, because what you'd want is for it to adapt to changes in the storage resources available and to the consumption rate. So if it never tried to go back up, the prefetch rate, then we might miss an opportunity to actually keep the consumer from waiting. And so you can see it goes back up, and then it realizes that it's overshot, and it goes back down, and it kind of starts to stabilize towards the end. And because it's bound by the storage, you don't see a lot in this graph. I mean, completed not consumed stays 0, but these lines are pretty, like, just basically what it's saying is that you're bound by the storage, not by the consumption rate of the, so you can actually see the uneven consumption rate in the done line. So the algorithm that we're developing now, the core premise of it is that it adjusts the prefetch rate based on the rate of change of completed not consumed. I mean, I use sampling and then set the prefetch rate based on that, and bias it towards more recent measurements of the completed not consumed change rate. And I also look at for storage bound workloads, I look at the difference between the prefetch rate and the in-flight rate, so that you kind of see how much of a backlog on either side are we building up and adjust for it. Now, the algorithm needs more work. It's difficult to come up with multipliers that work for fast storage and slow storage. It's also difficult to make sure that it ramps up quickly enough. So if you have a short scan, you don't have the time to wait to have the algorithm learn. And then, of course, need to implement it in Postgres and replace on the branch that AIO and DirectIO is on to start testing it and see if this method of feedback-directed prefetching actually works. And the simulator also still needs a lot of work. lots of features I want to add to it. So I'm looking forward to, and of course, we also need to do prefetching for other things than sequential scan. So there's lots of exciting work to do. I've listened to a lot of cache prefetching lectures, so I linked them here, even though it's not directly related to storage prefetching. There's the prefetch simulator code and also a link to the async IO and direct IO patch set.
All right, thank you very much, Melanie. Can you comment a bit on like the high level benefit of async and direct IO compared to the current IO layer for users?
Sure. So I think there are two major categories. One is that, so right now, all of your data is going to be in the kernel page cache and in Postgres shared buffers. So like, that's double the memory usage, right? So that's one of the big benefits. And then the other is, so the CPU overhead of doing all those mem copies just from the kernel page cache to the Postgres shared buffers, the CPU overhead of all the extra syscalls, because so with synchronous IO, you're doing a syscall for like every block, basically. So there's a lot of different benefits, and there's a lot, because Postgres knows a lot about data access that the kernel doesn't know, since we're a database. So I think we're going to see a lot of benefits for a lot of different types of workloads.
So what kind of workloads would benefit the most, and which would benefit the least?
Well, CPU-bound workloads may not benefit that much. Transactional workloads, I think, Andres has a talk about this. He has seen performance improvements for transactional workloads as well, for a variety of factors, probably a lot of them having to do with like decrease in the overhead. But you're going to see probably the biggest increase in analytical workloads, and especially for like high latency machines. So we have 3 milliseconds of latency. The benefit you get from asynchronous IO is big. So you're in cloud environments, you're going to really notice that. Got it.
So you talked a lot about not making too many IO requests to the operating system. So what actually happens if you make too many more IO requests than the IO device can handle? Do we get higher CPU, or does it actually block? What happens?
So it kind of depends, but basically, so if we won't make that many more requests, like there's caps and things like that. But if you let's say you use FIO as an example, just like to get away from thinking about it from Postgres point of view, and just make the queue depth really high and higher than, say, the IOPS of like a small Azure machine, then you'll just see really high latency. You'll see the latency go up and up and up. And as a Postgres user, that's going to translate to decreased CPS, definitely. But basically you're just going to see a decrease in performance. But the key for us is, if we're trying to prefetch a whole relation all at once, we're going to drastically decrease the performance of other concurrent workloads. Got it.
All right, very cool. And so I guess the question everyone will always ask, like, when does it going to be shipped?
Is Andres there? One of so AIO and direct IO are proposed for 16, which hasn't opened yet. The branch hasn't opened yet, but I would say that the benefits of like prefetching, that some of the learnings that we're getting from it, so just to clarify, AIO will also work with buffered IO. So some of the benefits that we're getting from it, like maybe we can take some of these learnings and use them in master, were AIO and DIO not to go in, but if they do, hopefully we're hoping for 16.
All right, that would be great. Okay, thank you very much.